Hi, Pat.
Hey,
Hey, how are you doing?
your name is
Oh yeah, Koji. It's Professor Koji Nakatokawa from Japan. So he has this professional account. So
okay.
he's letting us use it. Yeah.
You can change your name for this session if you want.
Oh
Just right
really?
click. Yeah.
Just click.
Right click your name. Right click the Koji Nakatogawa and
Oh,
then
I
just type.
see. Oh, rename it, right? Oh, okay.
Yeah.
Okay, I see. That's great.
Ali taught me that when I was testing it.
Ah, I see. Okay. Okay. It's good to see everyone here. Okay, so I think it's time, and it is my pleasure to introduce Patrick. Is it Lutz?
I pronounced it Lutz, but I think both are
Lutz.
considered correct.
Okay, so we have a pleasure to have Patrick Lutz to give us the second lecture. It's actually the 2.1 lecture on recursion theory. And then an hour later, we will have Jun Le Goh. So without further ado, I will pass it on to you, Patrick.
Can you give permission to the other?
That's right. That's right.
Other.
Yes. Yes. Okay. All right. So there you go.
So sorry, you need to give permission, I think, to my the other Patrick Lutz because I signed in with my tablet also.
Oh, I see. Okay. All right. Oh, you can give permission to yourself now because you're the host.
Oh, okay.
Yeah.
Okay. Oops. Okay, so I just want to start with a little reminder of some things I said at the very beginning of yesterday's lecture. So remember I said that the origins of computability theory, also called recursion theory, were this question by David Hilbert and some other people. Is there some just sort of mechanical procedure to decide, given any mathematical statement, is it provable or not? So can you like completely eliminate the job of mathematicians and just have a machine do it? So here's a little cartoon, like say you start with some mathematical statement and you feed it into the computer, then the computer should say whether it's provable or not. And so Hilbert was asking, is there some way to do that that just always works? And then I mentioned last time that Turing showed that this is not possible. So that was what we talked about at the very beginning last time. And then as a reminder, did we talk about the rest of the time? Well, first we defined this class of functions called primitive recursive, and then later a larger class of functions called general recursive. So the general recursive functions are the largest class of functions that take natural numbers as inputs and give you a natural numbers output, and which contain first these three basic types of functions, the constant functions. And last time, at least, I was denoting those Cn for the constant function with value n. It contains the successor function. And last time I was denoting that S. So this is the function that takes a natural number and gives you the natural number plus one. And finally, the projection functions. I was denoting these like P, K, I. This is a function that takes like K natural numbers and gives you the ith of those natural numbers. So those are all considered general recursive. And then the general recursive functions are also closed under first composition / substitution. So you can compose two recursive functions and get a recursive function. Second, this thing we talked about last time called primitive recursion. So you can give recursive definitions of functions, and that's still recursive. And finally, this last thing that separates the primitive recursive from the general recursive functions, minimalization. And last time I also referred to this sometimes as unbounded search. So in a programming language, this like corresponds to the ability to write while loops that have some condition for when they terminate, but you don't know in advance how many steps they might take. So we defined that, and then we talked about examples of primitive recursive functions. And then we finally defined Turing computability, and we discussed, though didn't really prove at all, the fact that general recursive is the same as Turing computable. And we also mentioned the Church-Turing thesis, which says that recursive, so I often refer to general recursive just as recursive. So it says that recursive equals our intuitive notion of computable. So you have some informal idea of what it means for a function to be computable, and the Church-Turing thesis claims that general recursive functions accurately capture that notion. And I want to comment that when people in computability theory or in logic more generally talk about computability, they usually don't go all the way back to the definition of something like general recursive or Turing computability. Instead, they write down something that is sort of intuitively computable and then claim by the Turing thesis that it is actually recursive. And anytime somebody has done that and then tries to write down the details, it works. So people are pretty confident they can sort of intuitively tell what's recursive or not. And so sometimes today I'll be doing that too. I'll want to prove that something is recursive, and I'll just kind of describe informally a computational procedure for computing it. So that's the recap of last time. And then one final thing that I want to remind you about. So we first talked about what it means for functions to be recursive, and from that we defined what it means for sets of natural numbers to be recursive. And they're simply recursive if their characteristic function is recursive. So the characteristic function of a set is just the function that gives you 0 if the input is not in the set, and 1 if the input is in the set. And so our first goal for today is to show that there is a non-recursive set. So to show that not every set is recursive. And by the Church-Turing thesis, this also shows there is a non-computable set according to the informal notion of computability. So that's the first goal for today. And what is this non-recursive set? Well, it's something called the halting problem, which is, the name is very famous, so you may have heard of it before. And the halting problem is the following problem. First, I'm going to describe it informally, and we're going to get a little more formal later. So informally, it's the problem that, the following problem, given a program P and an input X, does the program on input P on input X eventually stop and give an answer, or does it get stuck in an infinite loop or something and run forever? So does P of X eventually stop? Or does it run forever? So that's the problem. And the claim is that the halting problem is not computable. So there's no program that will take as input a program P and an input X and tell you whether P of X eventually stops or runs forever. So here's a sketch of the proof. It's by contradiction, so we suppose that it is computable. And then we'll define a program Q. So what does Q do? Well, Q takes as input a program P, and it checks whether P, when given input P, runs forever. So it takes the program P and feeds it its own source code as input. And if it runs forever, then Q of P will stop. And otherwise, if P of P eventually stops, then Q of P will run forever. So it will just enter some kind of infinite loop or something. And why is this program okay to write? Well, we've just assumed that checking this is computable. And how do we finish the proof? Well, we're just going to show that there's something impossible about the program Q. So the question we ask ourselves is, what does Q of Q do? So if we take the program Q and feed it as input, its own source code, what's going to happen? Well, if Q of Q stops, that means when we ran Q on Q, we should have entered this else case. And that means Q of Q should have actually run forever. On the other hand, if Q of Q runs forever, that means we should have entered this if case. We'll check if the input fed itself runs forever, and that means we should stop. So no matter what you assume Q of Q does, you can prove that it actually has to do the opposite thing. And so that's a contradiction. So we assumed that the halting problem was computable, and we got a contradiction by coming up with this program Q, which tries to do the opposite of what P of P is doing. That's the informal proof. Okay, here's a comment about it. What is the key idea of this proof? It's something called diagonalization. Basically, when we constructed this program Q, we took as input P, and we tried to make sure Q is not doing the same thing as the program P. And how did we do that? Well, we tried to do the opposite of what P does on some input. Which input? Well, just P itself. So this is some more like big trick in logic called diagonalization, and it shows up lots of places. So for instance, you may have heard of this thing called Russell's paradox, or this other thing, the uncountability of the real numbers. And those are two instances of basically the same trick. And if you look at the proofs really carefully, they're kind of exactly the same as this proof in some sense. So this is kind of like the only trick that logicians know, but it's super powerful, so it's good to know. Okay, what are we going to do next? We're going to make this argument slightly more formal. So you might wonder, how does this kind of connect to all this stuff about general recursive functions and so on that I talked about last time? Well, I'll try to show you a little bit about what the connection is. We don't really have enough time to develop it in complete detail. So the question, maybe the first question we have to ask ourselves to make this fit into our framework from before is, before we only talked about subsets of the natural numbers being recursive, or subsets of natural numbers squared or whatever. But the halting problem doesn't look like that. It's like a problem about programs and inputs. So how can we translate that into a subset of natural numbers so that we can actually ask whether it's recursive or not? Okay, so there's kind of a theorem that lets us do that. And I'm not going to prove this theorem, but I'll state it and mention something about how you could prove it. So the theorem basically says there's a computable enumeration of recursive functions. So there is some sequence of functions from natural numbers to natural numbers, f0, f1, and so on, such that first, all of these functions are recursive. And again, whenever I say recursive, you should understand it to mean general recursive. Second, every general recursive function shows up on the list. So for every recursive f, there is some n such that f is equal to the nth function on this list. And finally, this list is computable in the following sense, or recursive in the following sense. there is a recursive function from n squared to n such that when you give G inputs E and N, then it tells you what the ETH function in the list does on input N. So in some sense, G is telling you what everything in this list is doing. And by the way, these are actually not necessarily functions, but partial functions. So it's an enumeration of all the partial recursive functions. And similarly here, this function G is also partial. So these FNs are allowed to diverge on some inputs. They're allowed to have some places where they're not defined. Okay, so this theorem says that we have a recursive enumeration of all the recursive functions. And one final comment I want to make is here, I said for every recursive function, it shows up somewhere on the list. But actually, it could show up many times in the list. So that's allowed. So it's not like a list where each recursive function shows up once. It's a list where each recursive function shows up at least once and the whole list is recursive, but we could get a lot of duplicates. And in fact, you can show you have to get duplicates for this kind of thing. And what's the idea of the proof of this? Let me just briefly mention it. The idea of the proof is a general recursive function can be described as some finite sequence of the basic functions, like the constant, successor, and projections, plus which of those three operations you apply to get your function. So in general, a general recursive function can be described by a finite sequence of applications of those three operations. So every general recursive function is formed by starting with the constant, successor, and projections, and then like applying composition, primitive recursion, and minimalization to them. And so you record which of those operations you applied. And then we already mentioned last time that you can build up a bunch of recursive functions for dealing with finite sequences of numbers, and you can apply those here. Sort of like everything in this list is a different description of a general recursive function. And since you know how to deal with finite sequences and so on, you can unravel the whole thing and get this function G. That's maybe extremely hand-waving proof, but that's the idea. So how can we use this to make this theorem to make more formal this stuff about the halting problem? Well, we can define the halting problem as the set of pairs E comma N such that the ETH program in this list on input N converges. In other words, N is in the domain of FE. If you're worried this is a subset of N squared and I want to only talk about subsets in natural numbers, you can also fix that by picking a bijection between a recursive bijection between the natural numbers and the natural number squared, but it doesn't really matter, so I'm not going to mention that. As one final comment, maybe if you read books about computability, or i.e. recursion theory, you'll often see this list of functions written instead as phi0, phi1, phi2, and so on. So that's just some very common notation. It's not important. Okay, now finally, we have this definition, this more formal definition of the halting problem. How can we write a slightly more formal proof that it's not recursive? So the idea of the proof is exactly the same as before. So suppose H is recursive. And then define F from natural numbers to natural numbers by f of n equals, let's just say 0 if n comma n is an element of H, or sorry, not an element of H, and 1 if it is an element of H. And why is this a recursive function? Well, we showed last time that definition by cases is recursive. As long as you have a recursive set. So this set H we're assuming is recursive, and that means this whole, sorry, I messed up here. I meant to say diverges if n comma n is an H. Sorry, anyway, so definition by cases with the recursive set is recursive, we're assuming H is recursive, so this whole thing is recursive. And then both of these, the constantly zero function and the always diverge function, are recursive. And this is the same as what we said before. It's saying if program n on input n diverges, then we should converge. And if it converges, then we should diverge. So we're just doing the opposite of what program n does on input n. So now we said H is recursive implies F is recursive. So F has to appear somewhere on this list of recursive functions. So F equals FA for some A. And now we can just go through the same arguments before. So if F on input A converges, that implies that since F is FA, FA of A converges, which implies that A comma A is in the halting set. But that implies that what does F do on input A if A comma A is in the halting set? It diverges. So this implies F of A should diverge. So that's a contradiction. On the other hand, if F of A diverges, we can go through the same logic. So that means FA of A diverges, which means A comma A is not in the halting set, which means F of A should converge and be equal to 0. That's what we did in that case. And so that's a contradiction and ends the proof. Okay, so that's the slightly more formal version of the proof that the halting problem is not computable. And now I want to mention, how does this relate to the question we started with? So remember, we started with this thing. Hilbert asks whether there's a mechanical procedure for deciding if any statement is provable. And Turing said that's impossible. So how does the proof go? Well, here's sort of an informal version. We can actually reduce this question to the non-computability of the halting problem. So the informal proof is, suppose there was such a procedure. Then we could solve the halting problem. So what do? We're given a program P and an input X. And we want to decide whether P on X eventually stops or runs forever. And we have this ability, we're assuming this ability to computably check whether statements are provable or not. So we'll simply check whether the statement P of X eventually stops is provable. And then we'll say the same thing. So if it is provable, we'll output yes. And otherwise, we'll output no. And why does this work? Well, there's only one thing to check here, which is basically whether or not P of X halts is the same as whether or not it's provable that P of X halts. And you can actually show if P of X eventually stops, then that fact is provable.
Yeah, so I think we just lost Patrick. Let's just give him another few minutes. I think he should be back. His other account is still active.
Julia, I think meanwhile you can answer a question
Yeah?
in the chat.
Oh, okay.
I missed the previous lecture on set theory. Where can I find the recording?
Oh, yes, I'm still working it out. The previous lecture on set theory, I am trying to retrieve it. Once I have posted it, I will inform everyone. Okay. Yeah, Michael, I got your email. I have replied to you.
Hey, can everyone hear me?
Yes, got you now.
Okay, I don't know what happened.
Yeah, it happens.
Okay, it was yeah. Like suddenly on my computer, the Zoom window closed. I think I lost connection to the internet. Anyways, okay. Well, what I was saying is, if P of X runs forever, then it may not be provable that it runs forever. But if it eventually stops, that is provable. Okay. So next, I want to talk about something, an important concept in computability theory that arises naturally, I think, from this proof. So again, our proof was assume that we did have a way of checking if statements are provable. Then we could solve the halting problem by taking an instance the halting problem and turning it into an instance of this other problem. So there's some general idea in computability theory that captures when you can do that. So let me explain. Let's let A be the set of provable statements. And as a comment, we can think of A as a subset of the natural numbers. And what the way this proof works is there is a recursive function f from the natural numbers to the natural numbers such that n is in the halting set if and only if f of n is in A. And what was this function f really? It was just maybe let me write it like this. The function f, intuitively, it maps the input p comma x to the statement p of x eventually halts. And this was what showed that if A is computable, then so is H, because to decide whether n is an H, we just need to decide whether f of n is an A. And as maybe one last comment, I think I meant to say this earlier, how can we think of A as a subset of natural numbers? Well, we can list mathematical statements. We can enumerate them in some way. Let's say as psi 0, psi 1, psi 2, and so on. And then we could let the set A be the set of numbers such that the nth mathematical statement in that list is provable. So it's very standard in computability to, you have sets that are naturally not subsets of natural numbers, but you want to think of them as subsets of natural numbers just to make everything convenient, so that everything is about natural numbers instead of about programs and strings and whatnot. Okay, but the idea is really just, there is this function, this computable function that takes inputs, the halting problem, and turns them into inputs to this provability problem. And that's what lets you show that this provability problem is not computable. So now we're going to see how to generalize that. So we generalize it with this notion of many-one reducibility. So we're just going to be talking in the context of subsets of natural numbers. So we say a subset A is many-one reducible to a subset B. We write it A less than or equal MB if there is a function f like the one that we just saw. So if there is a total recursive function f from natural numbers to natural numbers, such that n is an element of A if and only if f of n is an element of B. And I want to comment here, it's sort of important, this is a total recursive function. And what does total mean? It just means it's defined everywhere. So it gives you an answer everywhere. Because if it were not total, then if we wanted to figure out A from B, we might be stuck, because maybe f of n would just never give us an answer. So that's the formal definition of many-one reducibility. The way you should think of this is sort of, there's a way of reducing solving A to the problem of solving B, or in other words, B is like at least as hard as A. So here's like a little example or a little picture to show what I mean. So the idea of this is basically, suppose that you had a kind of black box that magically solves instances of B, and you want to solve instances of A. So you want to compute A using your sort of magical black box for B. So you're this little purple guy asking, is n an element of A? What do you do? Well, you start with n, and you first turn it into f of n. And that's a computable thing to do because f is computable. Then you put it into your black box. The black box gives you some answer. Maybe it says f of n is not an element of B. And that tells you, well, the original n could not have been an element of A either, because n is an element of A if and only if f of n is an element of B. So then at the end, you figured out the answer and you're happy, n is not an element of A. And that's the idea, is many-one reducibility is one situation where you could sort of use a black box that solves B to solve A. And that means if you know how to solve B, you know how to solve A. So here's a theorem that makes that more precise. The theorem is, if A is many-one reducible to B and B is recursive, then actually so is A. And the proof is pretty much just this cartoon that I just showed you. So let's suppose f from the natural numbers to the natural numbers witnesses that A is many-one reducible to B. So it's a total recursive function, and n is an element of A if and only if f of n is an element of B. Then how can we compute A? So how can we show A is recursive? Well, let's note that the characteristic function of A, this is equal to 0 if if f of n is not in B, and 1 if f of n is in B. Because it's equal to 0 if n is not in A, and 1 if n is in A. Those are equivalent. And actually, you can even more directly just write the characteristic function of A is equal to the characteristic function of B composed with F. And we know that the recursive functions are closed under composition, and we know that F is recursive. So if the characteristic function of B is recursive, then so is the characteristic function of A. So that's the entirety of the proof. And as a corollary, and the way this is often used, say that you want to show a set A is not recursive. Well, it's enough to show how to reduce any other non-recursive problem to it. So if we show that H is many one below A, we already know that H is not recursive. That's what we just saw. That means that A is not recursive either. So when proving that things are not recursive, or if you're using the Church-Turing thesis, you can interpret that as not computable. It's enough to show that you can reduce the halting problem to them, or any other non-recursive problem. And as one final comment, you often think of this again as A is many one reducible to B means B is at least as hard of a problem as A. Okay, so what I just said again is to show A is not recursive, it's enough to show H is many one reducible to it. And this is like really the main technique for showing that things are not computable. So some things that have been shown to be not computable using this technique, well, we just mentioned the set of mathematical statements that are provable in ZFC. That set is not recursive. Next, the set of pairs of matrices A and B so that you can multiply them together in some order to get the zero matrix. So this could be like a matrix A and a matrix B, so that maybe A squared, B to the third, A, B to the 17, A is equal to the zero matrix. So that set is not recursive. The set of finite sets of tiles which do not tile the plane, that set is also not recursive. So there's no program that you give it a finite set of tiles and it will decide if they can tile the whole plane. And finally, the set of integer polynomials which have integer roots, that is also not recursive. And that's what Jun Le is going to be talking about. So that's like a very major theorem. But in the end, in some sense, it is proven by showing that you can many one reduce the halting problem to this problem. And what we're going to talk about next is some notion that encapsulates what's going on, or sort of some feature of all of these problems. So all of these problems are something which is called recursively enumerable. And I'm going to say next what that means. So that's some special feature of all these problems, not shared by all non-recursive problems, but shared by many important ones. So let me try to explain the intuitive idea of it before I write down a formal definition. The intuitive idea is, let's just start with the halting problem. The halting problem has this special property that even though we can't always solve it computably, there's some kind of computable procedure we have which, given an input to the halting problem, if that input is in the halting problem, the computable procedure will eventually see that it is. But if it's not in the halting problem, then maybe this procedure will run forever. And what is this procedure? Well, given a program P and an input X, we want to decide whether P of X, P comma X is in the halting problem. So let's just run P of X and see if it ever stops. So this procedure is, again, just run program P on input X, and if it stops, you know that the pair P comma X is in the halting problem. On the other hand, if it doesn't ever stop, you may never know for sure the truth about it. So the next fact is that every example I gave on the previous page actually also has that property. So I won't necessarily say it for all of them, but let's go back and kind of go through it. So the set of mathematical statements provable in ZFC, what's the procedure there? Well, just start sort of listing all possible proofs in ZFC. And each time you see a valid proof, like you know that that statement is provable. So if you're given a statement and you want to know if it's provable, you just start listing all proofs until you see a proof of it. If it's provable, you're eventually going to see the proof because you can, like, there is some way to enumerate all proofs. But if it's not provable, you may just never see anything and you could sit there waiting forever. Next, if you have a pair of matrices, how can you try to check if you can eventually multiply them together to get 0? Well, then just try all possible ways of multiplying them together. If there is a way to get 0, eventually you'll see it. If there's not, maybe you'll never see anything and you'll keep waiting forever, and so on. So each of these has this property. Like, there's some procedure where if a thing is in the set, you'll eventually see it. If it's not in the set, you might just wait forever. And sets with this property are, as I said, called recursively enumerable. And often this is abbreviated RE. And as a final comment, this goes by several other names. So a name that may sound more reasonable in the context in which I described it is semi-decidable. So decidable things are things where you can, like, compute whether or not anything is in the set. Semi-decidable is like if something is in the set, you'll eventually compute it. If it's not in the set, you might be stuck waiting forever. Sometimes it's also called computably enumerable. But these are all names for the same thing. So next, I'm going to give a formal definition of this. So a set A is called recursively enumerable, and RE for short, if, as I said, there's this kind of semi-decision procedure. So how do we write that formally? If there is a partial recursive function f, such that for all natural numbers n is in A if and only if f of n eventually gives you an answer. So if f of n is defined and the answer is 1. And as a comment, if n is not in A, then f of n may or may not be defined. The only point is if it is defined, it's not equal to 1. Okay, so we can, if n is an A, we'll eventually see it because f of n will eventually converge and give us the answer 1. And if it's not an A, then who knows what will happen, but we'll never be misled into thinking it is an A. So this is what recursively enumerable means. Next, I want to comment that there are several other equivalent definitions of recursively enumerable, and some of them may make the name recursively enumerable a little bit more reasonable sounding. So right now, it's maybe not clear like why this is enumerable in some sense. So I'm going to list 3 other equivalent definitions. So the first one is just a small variation on this definition. So again, A is RE if and only if there is a partial recursive function f such that n is an element of A if and only if f of n converges, and n is not an element of A if and only if f of n diverges. So here we just didn't really put many conditions on it if n was not an element of A. But in fact, we could have just said it never gives you any answer if n is not an element of A. How can you do that? Well, you can just modify the previous version. So take the function f from the first definition and modify it so if it ever converges, it's not equal to 1. Just instead make it go into an infinite loop. That's the first equivalent definition. The second equivalent definition explains why this is called recursively enumerable. So the second is there is a partial recursive function f such that A is equal to the range of f. So how can you think of this? You can think of this as like saying A is equal to the set f of 0 f of 1, f of 2, and so on. So that's the sense in which it's recursively enumerable. There's a recursive function which is like listing all of its elements, maybe not necessarily in order. And that's why it's not recursive. And the final equivalent definition is there is a recursive set which is a subset of n squared, such that A is sort of equal to some existential quantifier over B. So let me write what I mean by that. A is equal to the set of natural numbers n, such that there exists a natural number m, so that n comma m is in B. So sometimes we'll write this maybe, or people will write it as like exists m B. And this is another very useful way to think of recursively enumerable sets. They're basically sets which you can define with just using existential quantifiers and computable predicates. So there's some way in which recursive enumerability is sort of like a manifestation of the existential quantifier. So those are three equivalent definitions. Let me now just briefly sketch proofs that two of them are equivalent. So I'll sketch proofs that 1 and 3 are equivalent. And again, 1 was our official definition, and 3 is saying that A is the range of a partial recursive function. In other words, there's a partial recursive function enumerating all the elements of F, or of A, sorry. So first, let's prove 1 implies 3. So let's let P be a program. And again, I'm going to use the Church-Turing thesis a lot for the very last part of this talk. So I'm just going to sort of describe computational procedures and hope that you believe me that they can be turned into recursive functions. So let's let P be a program such that for all n, if n is an A, or sorry, maybe I should say it like this, n is an A if and only if P of n eventually stops and outputs 1. And now we want to get some program that will enumerate all the elements of A. So let's define a function f, and we're going to define it by recursion. And this function is going to be enumerating the set A. So f of n is going to be equal to, well, how does it work? First, we run P on 0 for one step. Then we run P of 0 and P of 1 for 2 steps each. Then we run P of 0, P of 1, P of 2 for 3 steps each. And so on. So we keep running more and more P on more and more inputs for more and more steps. And what are we waiting for? We're waiting for one of them to converge and output 1. So we're waiting for one of them to say that some number is in A. So we'll wait until we see P on some input stop and say 1. And as long as we haven't already used that M, we will halt and output M. So the idea is for everything that's in A, eventually P of that thing is going to halt and output 1. So eventually F will pick up all of those things. So that's the idea of the proof. Now let me mention a sketch of the proof of the other direction. So in this other direction, we start with the function f, which enumerates A, and we want to get a function which will like look at an individual element and try to decide if it's an A. So let f be a function whose range is equal to A. And now let's define a program P such that what does P do on some input N? Well, basically, it's going to look at the output of F on more and more values and wait if it and check if it ever sees N. And if it does, then it's going to output 1. So again, we're saying we can enumerate all the elements of A. So we want to decide whether N is an A. We'll just start enumerating more and more elements of A. And if we ever see that N is one of them, then we'll say, okay, N is an A. And if we don't ever see N as one of them, then we'll just end up waiting forever. So P of N, what does it do? It runs F of 0 for 1 step, F of 0 and F of 1 for 2 steps. F of 0, F of 1, and F of 2 for 3 steps. And so on. So it runs more and more values of F for more and more steps. So think of F as some program, I guess. And if F of N, or sorry, if F of M converges and equals 1 for some M, oh, sorry, I messed up a bit. So if F of M converges and equals N for some M, so if we ever see that N is in the range of F, then stop and output 1. So again, the entire idea is compute more and more things in the range of F. And if you ever see that one of them is N, then you know N is an A. So that's that proof. Now, I finally want to finish by mentioning some other important facts about recursively enumerable sets. A lot of these are easy to check, maybe not all of them. So if A and B are recursively enumerable, and C is also recursively enumerable, but in some higher dimension, then all the following are recursively enumerable. So first, A intersect B. Second, A union B. Third, the sort of existential quantification of C. So let's say exists MC, which we'll define as the set of n bar in n to the k, such that there exists an m in the natural numbers, so that n bar comma m is in C. So this is the same kind of existential quantification I talked about before. So the RE sets are closed under that. And they're also closed under bounded universal quantification. So let's define this as the set of n bar comma m in n to the k plus 1, such that for all x less than or equal to m, n bar comma x is in C. However, the RE sets are not closed under the following two things. First, complement. So the natural number is minus a. Remember, this is the set of things that are not an A. So even if A is RE, this set may not be. And second, unbounded universal quantification. So for all xc, this is the set of n bar in n to the k, such that for all m in the natural numbers, n bar comma m is in C. So those sets may not be RE, but maybe I probably won't prove any of these, but I want to mention one last theorem, which is kind of useful to know. if a set and its complement are both RE, then the set itself is recursive. So to compute a set, it's enough to sort of list out the elements of that set and at the same time list out all the elements of its complement. As a corollary, the natural numbers minus the halting problem is not an RE set. So you've seen that the halting problem itself is RE, so its complement cannot be RE because it's not recursive. So this actually shows you that an example of this first one. So maybe I want to finish by mentioning how you can prove this theorem. And again, just sort of a sketch, assuming the Church-Turing thesis and describing computational procedures, but not going back to the definitions of recursive. Okay, so let's suppose that A and its complement are both RE. So let's let F and G be functions which enumerate them. Sure. Maybe actually let me do it the other way using the original definition of RE. I think that will be slightly shorter to explain. So let's let P and Q be programs such that N is an element of A if and only if P of N eventually stops and outputs 1, and N is not an element of A if and only if Q of N eventually stops and outputs 1. Because N being an element of the complement is the same as N not being an element of A. And now we want to define a program which will compute A. So let's define a program R which does the following. So if R is given input N, it's going to run both P of N and Q of N in parallel. So what does that mean? Maybe it will run P of N for 1 step, then Q of N for 1 step, then P of N for 2 steps, then Q of N for 2 steps, and so on, until either P of N halts and outputs 1. So in that case, we know that N must be an A. We're in this top case. So we should halt and output 1 to say N is an element of A, or Q of N halts and outputs 1. In which case we know we're in the second case, so N is not an element of A, so we should halt and output 0 to say that N is not an element of A. And the point is, because every natural number N is either in A or not in A, one of these two cases must always occur. So one of those two cases always occurs, so either P eventually stops and outputs 1, or Q eventually stops and outputs 1. So one of these two cases always occurs. And they can't both occur on the same N because we can't have any N both in A and not in A. So this program I've just described will always eventually halt, and it will always output the right answer. And that means we've described a way to compute the elements of the set A. So yeah, that's the end of the lecture for today. I guess my suggestion is maybe we take like a 5-minute break before Jun Le starts his portion.
Yes, I agree with that. Thank you, Pat. Anyone has any question for Pat, maybe? All right, we can take a break for 5 minutes. Pat, you might need to. All right, yeah, work that out with Jun Le. You might need to make him host now.
Yeah, maybe get a host. Thanks.
Yeah. By the way, Pat, is the
Yeah.
recording on your computer or is it in the cloud? Do you know?
The recording?
Uh-huh. Are you did you record it? No, right?
So when I
you didn't
joined
start
the meeting, it
recording.
said it was recording in progress.
Right. You didn't start the recording, right?
I didn't start that.
Oh, okay. Yeah, I think it's in the cloud now.
I guess. Yeah, I don't know.
Yeah. Okay.
I'm not sure that I think I'm no longer host, although I'm still host on my iPad. So
Yeah. Jun Le,
I
your host now?
can. Oh, I think I can make Jun Le host from my iPad, maybe.
Yes, you
Yeah.
should be able to make him host.
Yeah, and I think you're the only one who can do that. So
Okay,
Yes.
it looks like you're host now.
great. Yeah, I think I am. Thank you.
All right. Cool.
Why is there no co-host
I
option?
don't know. I have no idea. It might be the setting, you know.
Yeah, that is weird. Yeah.
Yeah. I need to check.
Yeah, maybe if this is hosted by some particular university, then maybe that university has some policy that they cannot be
Yep.
co-host.
Could be. Yeah. It could be Professor Koji's university. Okay. Jun Le, you may start at any time you see
Well,
fit.
no, yeah, we say we're gonna take a 5-minute break, right? So yeah,
That's right, yes.
So I'm still waiting for that.
Yep.
Yeah, and now I first want to share my screen here.
Yep.
Okay, should be shared. People can see it, right?
Yep. Looks very nice. That's the
Great.
mascot for the Wisconsin Madison.
Yeah, that's right. That's Bucky the Badger. Yeah.
Ah, okay.
Also, I'm gonna put the link to the slides in chat so that people can have a look. Yeah, I'll say this again later, but yeah.
Yeah. So if you guys want to send me the your slides, your notes, and things like that, I can put them on the website. Yeah.
Yeah, I think I will do that once it's over.
When it's over. Yeah. Sure.
Yeah,
Yeah.
because I imagine there will be edits to be made along the way. I mean, right now these slides that I've made is only for the next hour. So
All right. Yeah.
yeah,
Sure.
and then I will kind of keep adding on
Mhm.
to the subsequent lectures. Yeah.
Yep. Yep. Cool. Is it snowing in Madison?
Not right now, but it's pretty freaking cold. Yeah.
Okay.
It's like minus 15 Celsius. Yeah.
Uh-huh.
So,
It snowed the entire day here in Boston.
oh, you're in Boston. Yeah. Okay. I was
Yeah.
wondering why you're in a winter coat. It doesn't make
Yeah,
sense. You're in Malaysia. Okay.
Uh-huh.
I see. Yeah. I think Boston definitely gets more snow than here. I think.
Yeah. Yesterday was good weather, but it started snowing since 4 in the morning.
Oh, okay. Right. Yeah. A few weeks ago, we went for like a walk on the frozen lake. So that was pretty
Oh,
nice.
nice.
Yeah. Do you think we should start?
Yep, go ahead.
Okay. Cool. All right. So, hi everyone. My name is Jun Le. I'm currently at the University of Wisconsin-Madison, and the goal over the next 5 hours or so of these lectures is to tell you about Hilbert's 10th problem and specifically its unsolvability. Before we start, let me just say that I've put the link to these slides in chat. That link will be updated as the lectures progress. So for now, this is just for today's lecture. I put it there in case you want to look at previous slides, like you missed some definition or you just want to look at it again, that might be helpful for you. And if you have any questions at all, feel free to stop me anytime. You can put it in chat or just ask on, unmute yourself and ask. All right, so the first thing is, well, what is Hilbert's 10th problem? I guess Patrick already kind of said what it is, but I'll say it again. So this here is a translation of Hilbert's original statement. So he had this list around 1900. He came up with this list of problems that he thought mathematicians should care about. And here's the 10th problem in the list. So given a Diophantine equation, which I'll say what that is later, with any number of unknown quantities and with rational integral numerical coefficients, the problem was to devise a process according to which it can be determined by a finite number of operations whether that equation is solvable in rational integers. So because this is like a translation from German, and also he was writing this around 1900. So whenever he says rational integral, we should really just be thinking integers, okay? So what we're looking at here is we're basically looking at a polynomial in a certain finite number of variables, and the coefficients of the polynomials are integers. And the question here is, well, if I give you such a polynomial, can you decide whether there is an integer solution? In other words, are there integers so that if you take the variables to have those integers, then the polynomial becomes 0? So this question, well, first of all, let me point out that this is not completely a mathematical statement as stated, certainly not in 1900, because, well, in 1900, there was no mathematical definition of a process which uses finitely many operations. And this is a case of something where, okay, if I actually come up with a process and I show it to you, probably we can all agree that that is a legitimate process, finite process, whatever that means. But, well, in this case, it turns out that as the title of my slides indicates, this problem was actually unsolvable. There is no such process. Well, if you want to show that there is no such process in a, and you want to give a mathematical proof of that, then you need to give a mathematical definition first of what a process is. And so this is what is provided to us by recursion theory, as Patrick has been discussing over the previous parts of the lecture. And here are some names, right, who contributed to this work: Gödel, Hilbert, Church, Post, and Turing. And I'd like to point out here that notice that this was only done after Hilbert posed his problems, right? So this was done in the 1940s, decades after Hilbert actually posed his problems. Now, so that alone, right, that there was a necessary step, but that alone doesn't resolve Hilbert's problem. It was only resolved later in the 70s by Matiasevich, who was also building on a lot of work of Davis, Putnam, and Robinson. So these people, their work together showed that there is no process to solve a Diophantine equation. So in other words, to determine whether it has integer solutions. Okay, so that's essentially our main goal of these series of lectures. I want to give you the proof of this theorem. So we haven't stated the theorem formally, but we will eventually. I want to give you the proof of the theorem. We won't see all of the details because a lot of the details involve elementary number theory. So there are a lot of things to check. But I want to give you at least the big steps of it and give you some flavor as to how the proof goes. Some notes about the references that I'm using here. So the references that I found most helpful for this are the following two articles. The first one is by Martin Davis. So the Davis from the previous slide. He wrote a nice article in the Monthly in 1973. Later, Jones and Matiasevich wrote another article with a slightly different approach. So the latter article has some kind of simplification of the proof. But I think both articles are great. So if you're interested in this, I recommend looking at both of them. And even though these are published in journals, if you just Google the names of these articles, you can find them like posted on somebody's website. So you can get these for free is what I'm saying. And in case it wasn't already obvious, so none of the results that I'll be stating are mine. So sometimes I will be sloppy about attributing results, but basically most of the results are due to a subset of Matiasevich, Davis, Putnam, and Robinson. Also, yeah, just, I guess since we're talking about references, at the end of the lectures, there will be a section discussing kind of future developments on Hilbert's 10 problem. So at first we'll focus on like developments in 1970 and before, but I also want to spend some time talking about what has happened since then, right? You know, people have been working on various questions. So when that time comes, I will give a list of references again with the more modern material. All right, so Diophantine equations. Let's just look at some examples, get some intuition as to what these things are and what Hilbert's 10 problem is. So kind of the most simple non-trivial example of a Diophantine equation is a linear equation. So we see here x plus 2y minus 3 is equals to 0. So we say that it's linear because each term in the equation has degree at most 1. Right? So the term x has degree 1, the term 2y has degree 1, and the term minus 3 has degree 0. So that's one example, a very simple example of a Diophantine equation. Another one here. So the first equation that I gave had 2 variables, x and y. Here's an equation with 3 variables. We could have x squared plus y squared minus z squared equals to 0. So this here, well, what are the solutions x, y, z to this equation, the integer solutions? Well, these are the Pythagorean triples, right? X squared plus y squared equals to z squared. So this is a very famous Diophantine equation, one could say. Instead of talking about squares, we could talk about cubes instead, right? So x cubed plus y cubed minus z cubed equals to 0. And of course, one could talk about this for any arbitrary natural number. So now we're going into kind of Fermat's last theorem territory, right? These are the equations that Fermat's last theorem is concerned with. Another example here, so going back to 2 variables now, but now we have degree 2. So this here is x squared minus 2y squared minus 1 equals to 0. This is a special equation. It's called Pell equation, and it's well, it is fundamental to the theory of solving quadratic Diophantine equations in general. So later in this series of lectures, we will look at Pell equations in detail. I'll give you a lot of basic facts about them. I'll prove some of them, but we will see this again. Finally, I wanted to give another fancy example here. So this here, y squared minus x cubed plus 36x equals to 0. This is an example of an elliptic curve. So you might have heard about these objects, right? These are things that, well, it's, I don't want to give the definition here, right? But the point is that this is something that number theorists definitely care about, and also has seen some applications in cryptography. So all of these examples on this slide, all of these are Diophantine equations. And so Hilbert's 10 problem in general is saying, well, if I give you such an equation, can you figure out whether it has integer solutions? Right. And for some of them, well, it's quite easy, sort of, you know, having hundreds of years of people having worked on them. For example, like say the second equation, right? We know that there are integer solutions. Likewise for the third, but actually for quite trivial reasons, because we could take x, y, z to be 0, right? So for the second and third equation, if you take x equals y equals z equals 0, then that's a solution. So sometimes it's very trivial whether individual equations have solutions or not. But the question here is, given any equation at all, is there a general process to do this? Okay, so I'd like to talk about a little bit about some classical results here. This will be very, very far from complete, but again, I just like to show you some results so that we get more intuition about what this problem is asking. So here are some examples of classes of equations which we know how to solve. So linear equation. Consider the linear equation ax plus by equals to c. Okay, so a, b, and c here are constants. They are integers. And the variables are x and y. Now, so you probably know from, I guess maybe from high school or maybe from first year university, you know that ax plus by equals to c has an integer solution if and only if the greatest common divisor of a and b divides c. All right, so one direction is quite easy. If you can show that for any x and y, the GCD of AB always divides AX plus BY. Right, so that's just like basic divisibility properties. And so that's one direction of this equivalence. The other direction, well, that's basically the Euclidean algorithm, right? So the Euclidean algorithm gives you a way of computing specific x and y so that ax plus by equals to GCD of AB. Now, GCD of AB might not be equals to C, maybe it properly divides C, but that's okay because once you have found x and y so that ax plus by equals to GCD of AB, then you can just scale that x and y in order to get the C that you want. So yeah, so in this case, right, it's sort of completely understood what's going on here. Either we can figure out that there is no solution, or in fact, we can figure out all of the solutions. Like we can just compute a general formula for all of the solutions here. So this equation here is very, very well understood. We don't just know how to figure out whether there are integer solutions, but we understand how the solutions look like. Okay, let's look at another case where, so this is, I wanted to give another example of how one might show that an equation has no integer solutions. A common method for this is to do what the number theorists would call reducing modulo p. So basically you take some prime number and you look at both sides of the equation modulo that prime number. So here's an explicit example of doing that. So let's consider the quadratic equation x squared plus y squared equals to 3z squared. Okay, so that's 3 variables here. And my claim here is that it has no integer solutions, x, y, z. So there are no integers x, y, and z, so that x squared plus y squared equals to 3z squared. Okay, so how may we prove such a thing? Well, so we're going to consider both sides of the equation modulo 3. Okay, so let's do a proof by contradiction here. So let's suppose that x, y, z is an integer solution of the equation. And for later purposes, so right now it's not clear why we want to do that, but for later purposes, it will be convenient to assume that the GCD of x and y is 1. Okay, so if x and y have any common factor, right, then we can just divide both sides of the equation by the square of that common factor, and you'll still end up with an integer solution. So we can clear that out without loss of generality. Now, notice that if 3 divides x, okay, so x is just some integer. We don't know whether 3 divides x or not, but if 3 divides x, then x squared is 0 mod 3, right? Okay, on the other hand, if 3 does not divide x, then x squared must be 1 mod 3. Okay, so this is basically the fact that if you take 1 and you square it modulo 3, you get 1. And if you take 2 and you square it modulo 3, you also get 1. So either way, x squared is going to be 1 mod 3 if it's not divisible by 3. The same is true for y, right? The exact same case division here. Now, notice that because GCD of xy is 1, so it cannot be the case that 3 divides both x and y. Therefore, the sum of x squared and y squared must be 1 or 2 mod 3. Okay, so basically there are 3 cases, right? Either x squared is 0 mod 3 and y squared is 1 mod 3, in which case their sum would be 1 mod 3. Or we have the symmetric case where x squared is 1 mod 3 and y squared is 0 mod 3. In that case, the sum is 1 again. Or it could be the case that x squared and y squared are both 1 mod 3, in which case their sum is 2 mod 3. And now the contradiction comes about by observing that, well, the right-hand side is divisible by 3. So then we get a contradiction. So this shows that this equation has no integer solutions. And it is, well, this is one of the, in a way, elaborations of this method is one of the main methods that number theorists have to show that integer equations have no solutions. Any questions so far? Okay, cool. So here are some examples of equations which we know how to deal with. Like, we were able to either decide when it has integer solutions or, show that there are none, things like that. Now, of course, there are many, many equations out there that we don't know how to deal with. So now let's we're going to start looking at abstract equations from now on. And let's talk about the theory that we need to build up in order to show that Hilbert's 10 problem is not solvable. The first thing that we're going to do is to kind of change the problem a bit. And this changing of the problem is something that's going to be convenient down the line. And also we are not actually changing the problem. Okay, so let me explain why. By the end of this slide, it should be clear what I'm saying. So first we have an observation here. Let's say we have a Diophantine equation P of x1 to xn. So x1 to xn are the variables. And we are saying, okay, we're interested in whether this P of x1 to xn is ever equals to 0 for any integers x1 to xn, right? So I'm saying that this first equation has an integer solution if and only if a closely related equation has a solution in the natural numbers. Okay, so what is this second equation here? Well, we're basically taking each of the xi's. Okay, so each xi is a variable, right? We're replacing it with the difference of two variables. So we take each xi, replace it with ai minus bi. Okay, so we're just basically performing a substitution, right? We take the original equation, we look at each occurrence of xi, we replace that with ai minus bi. And now we get a new equation, still Diophantine, right? All of the coefficients are still the same, so still integers. The number of variables has changed, right? The number of variables has multiplied by 2, but it's still a Diophantine equation. And now the point is that this second Diophantine equation has a solution in the natural numbers if and only if the first equation has a solution in integers. So the proof of this is really, I didn't even write it down on the slide because it's completely elementary, right? So if the first equation has a solution in integers, well, then you can write each integer as the difference of two natural numbers. So that gives us a solution for the second equation in natural numbers. And conversely, well, if the second equation has a solution in natural numbers, then the difference of any two natural numbers is an integer. So that gives you a solution to the first equation in integers. Does that make sense? Any questions here? Okay. All right. So that's one observation. Okay. Now, I'm hoping to go the other way as well. Okay. So what does this first proposition do? Okay. This first proposition says essentially that if we want to have a process for figuring out whether any Diophantine equation has an integer solution, it suffices to have a process for figuring out whether every Diophantine equation has a solution in natural numbers. Okay, because what do we do? Okay, let's say I give you an equation, P of x1 to xn equals to 0. Okay, you can transform it into this second equation by doing this variable substitution. And then if you were able to figure out whether this second equation has a solution in the natural numbers, then you can just give back the same answer, right? So Patrick just talked about many one reductions, and in fact, this is an instance of a many one reduction between certain sets. So I'm not going to give the formal details here, but I hope the idea is at least reminiscent of what happened earlier. Okay, but the point here is that this is only in one direction, right? So now we kind of want to go back in order to make sure that we're still working on a problem of the same difficulty. So in order to go back, well, what do we have to do now? So now I'm trying to say that, okay, if we have a Diophantine equation, and we are interested whether it has solutions in natural numbers, can we transform it into another Diophantine equation such that the second one has solutions in integers if and only if the first one has solutions in natural numbers? And we can do that, except that it is much less trivial to do it. So this I will call a theorem now. So now we're trying to do kind of the backwards process. So this first equation now, this P, we're interested in whether it has a solution in natural numbers. And this is the case if and only if this second equation here. So take each xi and replace it with the sum of squares of 4 variables now. So xi is replaced by pi squared plus qi squared plus ri squared plus si squared. Okay. And the claim is that the first equation has a solution in natural numbers if and only if the second one has a solution in integers. Now, one direction of this theorem is easy. So let's see which direction it is now. So if, right, so it's the backwards direction, which is easy, right? So if the second equation has a solution in integers, well, then we know that the sum of squares of integers is always a natural number, right? So any solution in integers to the second equation is going to give you a solution in natural numbers to the first equation. The forward direction, however, is a theorem. Okay, so this theorem says that this is a theorem of Lagrange from, I think, about 1800. So Lagrange showed that every natural number can be expressed as the sum of squares of 4 integers. So I've just kind of written it in a more symbolic form at the bottom. We're saying that, okay, for every c in the natural numbers, if you look at the equation, p squared plus q squared plus r squared plus s squared equals to c, it always has some solution in the natural numbers. So this theorem allows us to obtain the forward direction of the theorem, of the theorem above, because, well, if the first equation P has a solution in N, well, then take each of the xi's in the solution and use Lagrange's theorem to write it as the sum of 4 squares of integers. And so that tells us that the second equation has a solution in integers. Okay, so what's the kind of conclusion here? Well, the upshot of this slide is that now, instead of looking at Hilbert's 10th problem as originally stated, it's equivalent for us to look at the problem where we're asking for whether each Diophantine equation has a solution in the natural numbers. Okay, so we've changed the scope from integers to natural numbers when we're looking for solutions. And well, this is going to be technically convenient. So basically, we never have to worry about negative integers. So that's going to be just quite useful going forward. Are there any questions here? Okay, right. So now let's dive deeper into this. One of the key definitions of this whole theory is the notion of a Diophantine relation. So let's look at what this definition says. So we're looking at a relation which is n-ary. So it's a subset of n to the n. And we say that it's a Diophantine relation if essentially it is defined using some Diophantine equation. So we require that there is some Diophantine equation P, and the variables here, notice that there are two groups of variables here. There is the xi's and there are also the yi's. Okay. And we are saying that the xi's form a tuple, which is in the relation S, if and only if there is a tuple of yi's such that P of the x's and the y's is equals to 0. So here we're thinking of P as like the defining equation for this relation S. Also, I'd like to just again emphasize here that because we've decided to shift our scope from integers to natural numbers, so over here the existential quantifier over the yi's, the scope of that is the natural numbers, right? So the yi's must be natural numbers. The xi's must also be natural numbers as well. Okay, this maybe looks a bit abstract. So let's see some examples of the Diophantine relations. The first one, so here I'm just looking at a unary relation here. So we're looking at the set of natural numbers x such that x is not a power of 2. Okay, and I claim that this is a Diophantine relation. Well, in order to show that, I need to give you some Diophantine equation which defines it. And so I've written this an equation here. So the equation is x minus y times 2z plus 3 equals to 0. And why does this work? So think about what does it mean for a number to not be a power of 2? Well, that means that it must have some divisor which is odd and also at least 3. Okay, so let me say that again, right? X is not a power of 2 if and only if it has some divisor which is odd and is greater or equals to 3. So that's what we've expressed in this Diophantine equation, right? This 2z plus 3, well, that's always going to be an odd number. And because z is a natural number, right? So 2z plus 3 is always going to be at least 3. And furthermore, the converse holds as well, right? If you have any odd number which is at least 3, then it is equals to 2z plus 3 for some natural number z. So just by giving this equation here, right? So this shows that this relation is a Diophantine relation. Okay, let's see a few more examples. Here's another one. So again, I'm looking at the unary relation. So the set of all natural numbers x which are not prime. Okay, so what does it mean to be not prime? Well, it means that you can write x as the product of two numbers which are well, at least 2. So okay, I just realized that maybe there are some edge cases here that I forgot to think about. Namely, is whether 0 and 1 are considered prime or not prime. So if you just ignore those, okay, then then the equation that I gave works, right? So if you think about some number which is at least 2, and it is not prime if and only if it can be written as the product of two natural numbers which are each at least 2. So that's the y plus 2 and the z plus 2 in the equation. Okay, let's see a few more examples now. Again, of Diophantine relations. So here I've just repeated the definition from the previous slide. Well, so here's an example of a binary relation now. So we're looking at the pairs x comma y, which such that x divides y. So how can we define that using a Diophantine equation? Well, in order to say whether x divides y, that means that x divides y if and only if we can write y equals to dx, right, for some number d. So that's what we have done here. We can also talk about the ordering using a Diophantine equation. So if you have two numbers, x and z, well, x is less than z if and only if there is some natural number, which is at least 1, so that x plus that natural number equals to z. So that's what the v plus 1 is for, right? So if you're wondering why do we have v plus 1 rather than just v, well, that's because v could be 0, right? In which case x is equals to z. We don't want that. So that's why we have a v plus 1 to make sure that that term is at least 1. Now, this final example that I want to do here is a combination of these examples above. Okay, so here's a ternary relation now. So x, y, z, we want to say that x is the remainder of y when divided by z. Okay, so I claim that that's also a Diophantine relation. And we can express this by a combination of things that we've already discussed above. So, well, let's think about what does it mean for x to be the remainder of y when divided by z. Well, first of all, y has to be of the form q times z plus x for some quotient q. And furthermore, so that alone is not enough. Because that doesn't mean that x is the remainder, namely that, you know, x could be, for example, x could be equals to y itself, and the issue here is that x might not be less than z. Okay, so the remainder always has to be less than the thing that you're dividing by, right? So we also have to specify that x is less than z, in addition to that, to what I said previously. So now we have the situation where we have kind of two separate conditions that we want to specify. But we still want to specify them using a single Diophantine equation, right? This definition of a Diophantine relation, it only involves, you're only allowed to use one equation to define this relation S, right? You can't use like, the definition doesn't say that you can use a system of equations to do it. So, well, how can we get around this? Well, here's kind of a sort of a trick, right? So what we do is if you have a system of equations, okay, and you want to say, okay, these numbers satisfy all of them. Well, you can take each of them and take their square and take the sum of squares of all of them. So in this concrete example here at the bottom of the slide, right, what I've done is I've taken an equation, y minus dz minus x equals to 0. Okay, so that's an equation that would define whether y equals to the qz plus x, right? And I've taken the square of that, and then I've taken also the equation that defines whether x is less than z, so that is the x plus v plus 1 minus z. And I've taken the square of that, and I'm saying the sum of those two must be equals to 0. Well, so how does that work here? If you have two numbers and any two integers whose sum of squares equals to 0, then they must both be 0. Conversely, if you have, if you take 0 squared plus 0, that's equals to 0. So essentially, by taking the sum of squares, we can combine multiple equations into one. And that's kind of the sort of the trick that allows us to combine these to one equation to satisfy the definition. So yeah, so this last example shows that this remainder function is also Diophantine. Any questions here?
Jun Le, can we go back to slide number 6? I just want to clarify.
Yeah.
Yeah. How do we understand, like the second p and the function, right? No, the expression p of a1 minus b1 and so on, and also the other one is p of p1 squared plus q1 squared. What I mean by that is why don't oh, okay, I see. Yeah, so because it's the same p, right?
Right, it's
If
the
you
same P,
wanted,
yeah.
yeah, okay, so yeah. All right. So if you wanted to just write a1 comma b1 comma blah blah blah, that would require you to use another notation, right? For example, q.
Right. So
Okay.
there would be a different
Yeah.
different
That's
function. Yeah.
okay. I see it now. Okay, thanks.
Cool. Okay, so right, so we've seen a bunch of examples of Diophantine relations. Now, what we're going to do now is to talk about general properties of Diophantine relations. You're probably curious, hopefully, at least I hope you are, about, well, we've given a lot of examples of Diophantine relations. Now, a natural question is, what relation is not Diophantine? Right? I mean, like, if every relation was Diophantine, then this would not be a very interesting definition, right? So we're going to explore this question. Okay, and specifically, we're going to actually focus on Diophantine functions rather than relations. That will be much more convenient to work with. But that's where we're headed. And in order to understand that, we want to understand, well, just how much closure properties this class of Diophantine relations have. So as a starting point, a rather basic property we have is that the class of Diophantine relations is closed under intersection and also union. In other words, if I take two Diophantine relations and take their intersection, that remains Diophantine, and their union is Diophantine as well. So let's look at the proof of this lemma. Okay, so let's take two Diophantine relations and let's fix some Diophantine equations which define them. So notice that here I've stopped writing the variables individually, right? Previously I was writing like x1, x2, ... xn. But if the number of variables is not important for us, I'm just going to write like a single tuple x bar. And if you've attended any of the model theory lectures, then you should be quite comfortable with this by now. So we have these two equations here, and they may not have any relation to each other. The only thing that they have in common is that the x bar in both equations, that's the same x bar. Okay. Now, let's look at their intersection. Okay, we want to show that their intersection is Diophantine. So what does it mean? Like what is their intersection? Well, a tuple x bar lies in the intersection of S1 and S2 if and only if there exists y bar so that P1 of xy equals to 0, and there exists z bar such that P2 of xz bar equals to 0. Right, that's what it means to be the intersection of two sets, right? You satisfy the conditions that define both sets. And we just encountered such a situation on the previous slide, right? We had this example where we had like two conditions that define a set, two conditions whose conjunction defines a set, and we wanted to combine them, and we could do that using the sum of squares. So that trick works generally to show that if you take any two Diophantine equations, their intersection is Diophantine. So just take the P1 squared and P2 squared, sum them together. We want it to be 0. That's the definition of the Diophantine definition of the intersection. Okay, so this here is just we're applying this observation that we made earlier in a general context. Now, how about the union? Okay, so for the union, we have to use a different idea, right? Because now we are not saying that we want like the first equation to have a solution and the second equation to have a solution. Instead, we're saying, well, we want the first equation to have a solution or the second equation has a solution. Now, so that actually can be accomplished in an even easier way. So what we do now is, so if we want to define a union, well, then we take the product of the two equations. All right, so if you take P1 of xy times P2 of xz, if we want that, if that's equals to 0, well, then we know that at least one of them must be 0. And that means that at least one of the equations has a solution. Conversely, if one of the two is 0, then certainly the product is equal to 0 as well. So this here shows that this class of Diophantine relations, at the very least, is close under intersection and union. And we will see that it has many other closure properties. Yeah, that will take quite a long time to show. So that's kind of the goal of like the next 2 hours, 2 or 3 hours in these lectures. Okay, so yeah, like I said a few slides ago, for the next 2 hours, maybe, we're going to be focusing on Diophantine functions. So these here, these are simply functions whose graphs are Diophantine relations. And I'd like to emphasize here that we're talking about total functions here. Okay, so these are total functions from n to the k to n. Here's a lemma. So about closure properties of Diophantine functions. We claim that they are closed under composition. And that's actually not hard to show. Doesn't even require any number theory at all. So let's see the proof. So let's suppose that we have an M-ary Diophantine function f. So f takes in m natural numbers and it outputs one natural number. And let's suppose that we have also G1 to Gm, and each of the G1 to Gm are n-ary. So each of the G1 to Gm, they take in n natural numbers. Okay. Actually, I guess, yeah. So over here, the arities of the GIs don't have to be the same, but okay, that's fine. The proof is the same either way. Now, what I've written here in the displayed equation, you can see this is the composition, right, of the f together with the G1 to Gms. And so now we want to come up with a Diophantine definition, right, of what does it mean for z to be equals to f of G1 to Gm. Okay, so what can we do here? Well, we know how to specify that z is equals to f of like certain numbers, right? But then those certain numbers, well, those are just variables that we don't have control over. And in order to specify that this is like z is obtained by the composition, right? We want to say that those certain numbers are in turn outputs of g. So basically, what we're going to do here is we're going to introduce new variables, and those new variables are going to record the values of g, and it's going to help us figure out, whether f of those new variables is equals to z or not. So okay, that probably sounded quite vague. So here's explicitly what I'm trying to say. So I'm introducing m new variables, y1 to ym. Okay, and the idea here is, well, if you see in the equation, y1, we want it to be equals to g1 of x1. And likewise for y2 and y3 and so on. And so if that is true, and z is equals to f of y1 to ym, then we just combine all of those things together, right? Then we get the original line above, right? The fact that z is equals to f of g1 dot gm. So this second guy here is really just a restatement of the first guy, but the good thing now is that this thing here, the stuff after the existential quantifiers, that we know how to define in a Diophantine way, because we have Diophantine definitions for f, and we also have Diophantine definitions for all of the GIs. So I'm not going to write out the details here, but the point is that you take each of the Diophantine definitions of f of GI, you substitute it into the thing, so you're going to get much more. You're probably going to get more variables than just y1 to ym, right? Because the Diophantine definitions themselves have existential quantifiers. So you will get more existential quantifiers, but all of them are existential, so that's okay. And in the end, you get a Diophantine definition of the composition. And the part of the reason why I'm not specifying details is because these substitution has to be done with care, because you have to worry about whether there's conflict between the different Diophantine definitions. If they have variables in common, you want to do some renaming of the variables to avoid the conflict. Otherwise, you end up specifying some dependencies that you didn't want to. So there are some minor details here, but hopefully you believe me that this can be done. Any questions here? All right, so we've showed some basic closure properties of the Diophantine relations, and now the Diophantine functions. Now let's go to the beginning of the first section of this series of lectures. Now this section will be a very long section. I think it will take 2 hours at least. And the main result, so I like to just end today by telling you what the main result is in this section. And then we'll start on the proof next time. So as the title indicates, the main result here is that Diophantine is the same thing as recursive. So up until now, right, we haven't mentioned any notions from recursion theory at all, except on the very first slide. But it turns out that, well, recursion theory kind of organically arises over here. And so let me be more precise here. So the main theorem of this section is to show that the Diophantine functions are exactly the recursive functions. Okay, those are the same class. That despite, so like, I don't know, like why is this cool? Like the fact that, okay, if you look at the definition of Diophantine functions, well, there's nothing about recursion theory in there, right? This is entirely about integers, polynomials with integer coefficients, having integer solutions, having natural number solutions. There's nothing about recursion theory in there, but somehow it yields something which agrees with something from recursion theory. So I think this is very remarkable. And it's also something that happens in a number of places in mathematics. So not just in Hilbert's 10 problem, but also in other mathematical objects. Right? People have studied things which turn out to have connections to recursion theory, even though the original definition did not. So that's the main theorem that we'll be working towards. There is a lot of setup that we need to do in order to prove this. But just to end off today, I'd like to talk about the easy direction of this theorem. So the forward direction is very easy. It's going to be on this slide. So every Diophantine function is recursive. Okay, let's look at the proof here. And this will be a bit of a sketch, well, because again, we're kind of using, I'm not giving a formal proof, like I'm not giving a formal kind of expression of the Diophantine function as like the composition of minimization of things, right? So I'm just going to kind of give you the idea as to why it's recursive. So let's suppose that f is a Diophantine function. So again, reminder that a Diophantine function is one which has a whose graph is a Diophantine relation. So what this means is that z is equals to f of x if and only if there is some tuple y such that p of x, z, y equals to 0. So p here is a Diophantine equation. And f here is a total function. Okay, so for every x bar, there is exactly one output z, so that this is true. Now, why is this recursive? Well, so basically what we're going to do is we're going to do, and to find z, okay, let's say if I give you x bar, and if we're trying to show that f is recursive, well, then we should be able to compute z, right? So what's the algorithm for computing z here? Well, basically we're just going to do an unbounded search, okay? And what are we searching for? Well, we are searching for z, right? But we can't exactly search for z directly because the condition that defines z is not computable. But the condition that defines z is it has an existential quantifier over a computable thing. So what we're going to do is that we're going to search for some witness y. So I'm thinking of y as like a witness for the fact that z is equals to f of x bar. Okay. And the point is that we're going to look through all of the possible tuples y in some systematic way. Okay, we're going to test each of them. Like, okay, we take some y bar, and then we're going to see, okay, is p of x bar z y equals to 0? And that's something that we can compute in finite time. We get an answer, yes or no. If the answer is no, then we just move on to the next tuple y. And then we ask the same question again. And also, we're doing this in parallel for all of the z's, like all natural numbers z. So this is something that you have to do a bit of bookkeeping to arrange it in an appropriate way. But the point is that eventually you will find some y bar so that p of x, sorry, you will find some y bar and you will find some z so that p of x bar z y equals 0. And once you have found such y bar and z, then you know that z is the correct value. You know that z must be equals to f of x bar. So what I've just described is essentially an algorithm. Of course, more formally, you want to use the minimization to do that, but hopefully it conveys the idea. So that's one direction of the theorem. And so next time, we're going to start by talking about the opposite direction, which is going to be a very complicated affair. But yeah, thanks for listening, and I'm sticking around for questions.
Yeah, thank you, Jun Le. Any question? Yeah, I really look forward to the other direction of the proof.
Yeah,
Yeah,
I mean, it was it's
Uh-huh.
it's pretty fun. I mean, so let me admit that I wasn't fully aware of a lot of the aspects of this proof before preparing for these lectures either. But
Ah,
yeah, it's been fun to read up and learn
uh-huh.
about this. Yeah,
That's right.
Yeah.
We have a question in the chat. You want to take a look?
Yeah, let me see. Okay, yeah. So it is true that a lot of the things that I'm saying here is would be considered part of number theory. But the thing is that I guess if your question applies to recursion theory as well, then I'm not really sure. Like, so do you think that recursion theory relates to logic? I guess that would be that would affect my answer to you, Michael.
I'm not sure that it does. I can definitely see model theory and proof theory as part of logic.
Mhm.
But to me, logic stops before set theory, and everything that is in recursion theory that I've seen so far, or in or set theory, to me is above logic. It's not actually part of logic. They may be part of the foundations of math, but you have well-founded set theory, you have non-well-founded set theory, you have category theory. Those are all different possible foundations of mathematics, but they're all built on top of logic itself. So,
So I think, yeah. So yeah, thanks for sharing your views here. And so based on your response, I think it's quite clear that I think we see the word logic quite differently. So
well, I guess that's my question. How do you see logic that? What is your view of logic that includes this? You know, how do you get from propositional logic or predicate logic, paraconsistent logic, or paracomplete, or intuitionist logic, or the study of those to this?
Yeah. Okay. So I can give a concrete answer, at least for recursion theory. Okay. And so if you take the language of arithmetic and you look at so look at what subsets of the natural numbers are definable in this language using a first order formula. Okay, and if you only look at the formulas which of a limited complexity, then you're going to get the recursive sets. And if you look at a different complexity, you're going to get the recursively enumerable sets, and so on. So you can go even higher. This is what we call the arithmetic hierarchy. So actually, recursion theory is intimately connected to these hierarchies of definability in arithmetic. So I think, to me, that's a very concrete connection between, yeah.
Yeah. I just want to add, I believe that, Kat Slayman thinks of recursion theory as definable arithmetic, right? Something like that.
Yeah, right. And no, it's a study of definability. Yeah.
Yeah, from many of his writing and what I heard from other people as well.
Yeah, he gave a Godot lecture in 2000 about that. Yeah.
But even arithmetic is something that's built on top of logic as a separate object system. So it still seems, and of course, number theory is directly related to arithmetic. I mean, all of this is interesting. I'm just.
So I don't understand what you mean when you say that arithmetic is built on top of logic. So do you
have
not
an extra
consider like what is first order logic to you?
Okay, well, first order logic is basically your predicate logic with your predicates, your first order, your quantifiers, but you can have second order logic. You can have variations on logic, and like I say, there's a whole lot of areas like model theory and proof theory that are directly studying logic itself. Okay, but it seems to me that a lot of this is studying systems that are built on top of basically classical logic, which is only one of the many logics that might be out there or that might be used. Sure. Even proof by contradiction could be considered to be controversial in some places or in some logics.
Sure. Yeah. I mean, that's fine. And that I consider, like, the study of non-classical logics. I consider that part of logic for sure, but I don't consider that the totality of logic, unlike you. Yeah.
Right. Well, I mean, it's just my view may not be broad enough. And so, yeah, I'm kind of.
Well, no, I think, I think it's, your view is broad in a different direction, I would say. Yeah. So, yeah.
Yeah. Also, if I may add, I organized this course series based on the understanding that logic consists of. Logic is built of the four pillars, right? You have you have proof theory, you have a model theory, you have set theory, and then you also have recursion theory. So that's my idea of the term mathematical logic.
Right.
If that answers your question, Michael.
Right, right. And I'm not questioning how it's put together. It's just that
Yes.
my view may not be broad enough to include it. And the question is, maybe I'm missing something. I need to broaden my view.
Yeah.
Or maybe I'm really just more hyper focused on part of it.
Yes. I think you have a really valid question, Michael. Because I used to think like that as well. Like 20 years ago, before I really got into logic, I was also thinking about what you were thinking. But then I sort of got used to it and just accept what the status quo. But I think, maybe Jun Le and the rest of the other speakers might have a better explanation for that.
Yeah,
Okay.
well, I don't know if I have anything better than what I just explained, but yeah. I mean, for me, it's like I see math logic as in a way a branch of math, right? I don't see logic and math as separate. So
yeah,
yeah.
In a way, I think I understand both your standpoints.
Yeah, right.
I used to be like Michael at this moment. But then later on, I sort of accepted it as a branch of mathematics, like you.
Right, and I think maybe part of it is also just sociological, right? Like the people who go to the same conferences and publish in the same journals, So.
Yep.
Yeah, and at this point, I've got a bachelor's in math, and I'm planning on applying to grad school. Is interest in my definition of foundations of math, which might include alternative set theories or whatever, but also alternative logics. And so these other things would be kind of things I would encounter in my number theory class a lot, or in concerned about all the different ordinals and everything. And that's all part of a lot of that's part of the, like set theory especially, is part of the foundations of mathematics, because everything is built on top of it. But then it itself is an object theory on top of, I guess more pure logic. To me, logic, you don't know anything about the subject. I don't remember the quote, but math is something where you don't know what you're talking about and you don't know if it's true. Just due to abstraction. And I'm sure 100 years ago or more than that, there was no distinction whatsoever between math and logic. They didn't even think about logic until they started having to worry about the paradoxes, and then they kind of separated it out, and they didn't even distinguish between first and second order logic. I mean, that kind of separated out too. But then they added, set theory as a foundation for everything else. And model theory and proof theory have come a long way, although a lot of them seem to assume that you have to have the natural deduction theorem. And if you don't have it, it seems like a lot of that doesn't really work very well. But it also seems to me that like in set theory, we went away from naive set theory and we kind of painted ourselves into a corner where we hope everything is okay, but we can't really look at everything around it, that just because it might be inconsistent. But still, like I say, maybe I'm more hyper focused on the bottom layer, but that's what I've always understood logic to mean. And when I read different books on logic and whatnot, they don't really even get into set theory or recursion theory. I see it in, of course, in things like computer science, but and of course, number theory. But like I say, is possibly that I just need a more broader outlook.
Yeah, well, I think your outlook might be common amongst like philosophers, for example. Philosophers who work in logic. I think that these are the kinds of questions that they care about. But in terms of mathematicians, I think, yeah, like I think most if not all mathematical logicians would have the same viewpoint as what Tu Yao and I have said. Yeah.
Mm-hmm. Yeah, yeah. I think when yeah, I mean, way back when I didn't know what mathematical logic is like. I mean, at least not the community of mathematical logic is like. I was also thinking along the lines of philosophical logic, and yeah, I think that explains. I think it's more of a cultural thing now that you have recursion theory and set theory in as part of mathematical logic. I think it's just a play of names, in my opinion, maybe.
Well,
Yeah.
it could be, and as I gain more experience, you know, I could wind up shifting my viewpoint some.
Yeah, I think that might happen actually.
Yeah. Anyway, it is getting late for me, but yeah.
Yeah.
So I should go and sleep soon.
Yes. Thank you, Jun Le, and thank you everyone for coming. And is Pat still around? I also want to thank Pat for being here. Nah, he's not here anymore. Okay, so thank you. I'll see you again.
Great.
Jun Le.
Yeah. Hope to see you all next time.
All of you. All right. Bye-bye.
Bye.